Section 3.6 is on perpendiculars and distance. The distance between a line and a point not on the line is the length of the segment perpendicular to the line from the point. In other words, there are an infinite number of lines that I can draw from point P to line L, and those are represented by these some of these dashed lines here. But I can just draw a whole number of lines there. But the line that represents the distance, the segment that represents the distance, is the segment that is perpendicular to the line. So we'd say that the distance from point P to line L is the length of segment PS. It's not going to be the length of another one of these segments here, but it's going to be the one that is actually perpendicular to the given line. The perpendicular postulate says that given a line and a point not on the line, you remember that's similar to the parallel postulate we had before, but if you have a line, so like line L, and point P, which is a point that is not on line L, there exists only one line that goes through the point that is perpendicular to the line. So while there are an infinite number of lines I can draw through point P, there is only one line that is going to be perpendicular to line L. So here's a couple examples. Draw the segment that represents the distance from point P to segment AB. So while I can draw a whole bunch of different lines from P to AB, the segment that represents the distance is going to be the one that is perpendicular to it. So draw it like that, and then put the little box in the corner to show that it's perpendicular. If you're having a hard time seeing this, you might actually want to I kind of like to turn my paper around so that the point I'm starting at is at the top, and just picture it dropping straight down. Second example here is a little tricky. The segment that represents the distance from point P to AB is actually going to be this segment right here. It's perpendicular because I can extend AB out this way, and then now this segment from P straight down to the extension of line AB is the segment that represents the distance. Now, here's a really tough problem, and there's a lot of steps, but I think we can do this. Find the distance from point P to line L if line L contains the points 4, 3 and 2, 0, and point P has coordinates 3, 10. Before we dive into this and go through all of these steps, let's take a look at what we're saying here. Here is line L, and it has those 2 points on it, -2, 0, and the point 4, 3. And up here at 3, 10 is point P. I need to find how far is point P from line L. So in other words, I need to find the length of the perpendicular segment from P to L, kind of represented by this right here. So the first thing I need to do is figure out what is the slope of line L. Okay, so I'm going to need to find the slope of that line, because the slope here is going to be the line that's perpendicular to it. Actually, not just the slope, let's write the equation of that line. So let's start by finding the slope of line L. So that's going to be 0 minus 3 over 2 minus 4. Did I do that right? 0 minus 3 over 2 minus 4 is going to give me, oh, I'm sorry, oh, sorry, I made a mistake in copying this problem. This should actually be a -2 right here, which is what I had on my diagram here. Yeah, -2, 0, my mistake. Did you catch that? So this point right here should be a -2, 0, not a +2, 0. So let me back up a little bit. Doing my slope, I'm going to do 0 minus 3 over -2 minus 4, which is going to give me a slope of +1/2. Okay, so that's the slope of that line, but I would like the equation of that line. So I'm going to use either point. Maybe I'll use this one right here. Plug that into y equals mx plus b. So y equals m times x plus b, and I need to find my b. So my b is 1. So the equation of line L is y equals 1/2 x plus 1. So that's the equation of line L. I'll be using that in just a minute. Now I need the equation of the line that's perpendicular to L through point P. So what I need is the equation of this kind of line going here from P going down to L, and what is its perpendicular. Well, I know what the slope of that line has to be. Since it's perpendicular to L, it needs to be the opposite reciprocal of the slope of line L. So the slope of L is 1/2. So the perpendicular slope that I'm going to use has to be a -2. So the slope of the line from point P going this way towards line L, the slope of that line has to be a -2. And I know a point on that line. I know at the point P, which is 3, 10. So let's plug that into y equals mx plus b. So y equals m times x, and let's find our b. Or 10 equals -6 plus b, so b is equal to 16. Then the equation of that line is y equals -2x plus 16. -2 was my slope, 16 was my y-intercept. So now I have those two equations. So what I need to do next is solve this system of equations to find at what point these two lines intersect each other. Let me show you here. So I know the equation of L. In fact, maybe I'll go ahead and fill that in. That's y equals 1/2 x plus 1. And then I know the equation, that's a little sloppy. I know the equation of this line going this way. That's going to be y equals -2x plus 16. But I need to figure out where do those two lines intersect each other. Maybe I'll just kind of do a little dashed line so we can see what's going on here. Okay? What is the point, the exact point where those two lines intersect each other? To do that, I'm going to solve a system of equations. Since both of them are equal to y, I have y equals 1/2 x plus 1 and y equals -2x plus 16. I can set both of them equal to each other. The top one equals y, the bottom one equals y. So I can say 1/2 x plus 1 equals -2x plus 16. And let's solve that for x. Oh, probably the easiest way to do that is to get rid of that pesky fraction and multiply everything by 2. So that's going to give me x plus 2 equals -4x plus 32, or 5x is equal to 30, or x is equal to 6. That's the x coordinate of the point of intersection of those two lines. Let's plug that into either equation. Let's plug it into, maybe I'll go ahead and plug it into the first one. I'm not too afraid of that fraction. So y equals 1/2 times 6 plus 1, or y equals 3 plus 1, or 4. So the point of intersection of those two lines is the point 6, 4. When I solve that system of equations, I figure out where those two lines intersect, and that is, I'll go ahead and graph that on here. That is the point 6, 4. And actually, I didn't draw my lines very well, but that's the point right there. That's the point of intersection, 6, 4. Now, I know the coordinates of P, which is 3, 10, and I know the coordinates of the point of intersection. Now I just use the distance formula to figure out how long this segment right here is. Maybe I'll do it in blue. How long is this segment right here? That's what I'm looking for, how long that is. So to do that, I will use the distance formula. And so I have the point 310 and the point 64. So remember, the distance formula is x2 minus x1 squared plus y2 minus y1 squared. Okay. Or the square root of 3 squared is 9, plus the square root of -6 squared is 36, or the square root of 45. Don't give me a decimal, simplify that. Remember how we did this in Algebra 1, simplifying radicals? So that's going to be equal to 3 square root of 5. So the distance between line L and point P is 3 square root of 5 units. And notice, there's no way you can count boxes because that line is going diagonally. Okay, so lines are parallel if they never intersect, or if they are everywhere equidistant. So notice this is kind of like an extension of the definition of parallel. They never intersect each other, but their distance between them is the same everywhere. Also, the distance between two lines is the distance between one of the lines and any point on the other line. In the last example, we were taking a look at the distance between a point and a line. Here, if we're talking about the distance between two lines, we're going to pick one point on one line and then find the perpendicular to the other line. So the distance between line L and line M is the length of segment PR. And here's another last example. We need to find the distance between these two lines. Y equals negative 2x plus 4 and y equals negative 2x plus 14. Notice these two lines are parallel to each other because they have the same slope of negative 2. And in fact, here's a picture of what they look like. My lines aren't super straight, but you kind of get the idea. Here's the line y equals negative 2x plus 4. Here's the line y equals negative 2x plus 14. I need to find what is the distance between those lines. What is the length of a segment that is perpendicular to each of those lines? So to do that, first thing I need to do is to write the equation of the perpendicular line. Okay, so since the slope of these lines is negative 2, the perpendicular slope is a positive 1/2. Now I need a point on one of the lines. Probably the easiest one to use is the y-intercept of the first line, which is negative 4. So the point 0, 4 is the y-intercept of the first line. And that's a point on the line y equals negative 2x plus 4. In fact, let's go ahead and mark that here. In fact, I already have it marked. That's this point right here. And so I'm going to be going this way. I'm going to be looking for the length of the segment that goes from the y-intercept here over to my other line. Okay, so the equation of that perpendicular line is going to be y equals 1/2, because I need the perpendicular slope, x plus 4. It can have the same y-intercept, so that's the equation of that line right there. Okay, so now I'm going to solve a system of equations to find the intersection of that perpendicular segment and the other line. So I'll just do a little sketch coming off of this. Here's the line, there's a little segment, and I don't know if that's exactly perpendicular. That's the segment that has the equation y equals 1/2 x plus 4, but I need to find what is this exact point where they intersect each other. So I'm going to solve a system of equations that uses y equals 1/2 x plus 4, and this second line right here, y equals negative 2x plus 14. So between y equals 1/2 x plus 4 and y equals negative 2x plus 14, let's solve that system like we did before. So since both of those equations equal y, I can set them equal to each other and solve for x. And again, maybe I'll just multiply everything by 2 to get rid of the fraction. Oops, not 14, 28. I was going to say that didn't look right. Adding 4 to both sides, subtracting 8 from both sides. So x is equal to 4. Then I'll plug that back into my first equation. 1/2 times 4 plus 4, or y equals 2 plus 4, or y equals 6. So the point of intersection between the two lines is the point 4, 6. Let's take a look at my graph and see how close I was to that. Not very close. So the point 4, 2, 4, 6. Oh, it's actually this point right here. I'm going to go ahead and erase what I did before. Okay, so that's this line right here. That's the point 4, 6. This is the point 0, 4. Now to find the length of that segment, I'm going to use the distance formula. So using the distance formula on 0, 4 and 4, 6, I get the distance equals the square root of 6 minus 4 squared plus 4 minus 0 squared, or the square root of 2 squared, which is 4, plus 4 squared, which is 16, or the square root of 20, which simplified, that's a 4 and a 5. Simplified gives me a 2 square root of 5. So the distance between these two parallel lines is 2 square root of 5 units, because that's the length of the perpendicular segment between those two lines.